Today we study ESA6H, Cartesian coordinates and Euclidean space. Until now, we have studied how to compute the area of a parallelogram spanned by two vectors, A and B. And the area of this parallelogram is a product of the magnitudes of two vectors multiplied by sine theta, where the theta is the angle between the two, and base times the height, so a b magnitude multiplied by a magnitude sine theta, that is the height of this parallelogram. And if we make use of the scalar product A dot B, that is proportional to cosine theta, and applying Pythagoras theorem to find the Heron's formula for the area of this parallelogram. At the end of the day, we have found the expression that is sum of squares. Sum of squares. That is A2, B3, this one, and this squared, and this squared. So we have found this is something like the magnitude of a vector whose Cartesian components are this, this, and this. Sure, there is an ambiguity of plus minus, plus minus, plus minus. Because this is all squared expressions, we don't know what the exact sign of that vector represented by the magnitude determined by the Heron's formula. For simplicity, among 1 to 8 possibilities, we choose only a single vector whose direction is completely determined by this positive sign, plus, plus, plus. The first Cartesian component, the x component of this vector, is A2b3 minus A3b2. And the second component is A3b1 and A1b3. And the third one is A1, B2 minus A2, B1. It has a special feature that if we consider these vector indices, they consist of only a single 1, single 2, and single 3. So 1, 2, 3, 1, 3, 2, 2, 3, 1. 2, 1, 3, 3, 1, 2, and 3, 2, 1. In addition, 1, 2, 3 has a positive sign. 1, 3, 2 has a negative sign. 2, 3, 1 has a positive sign, but 2, 1, 3 has a negative sign. 3, 1, 2 and 3, 2, 1, they have opposite signs. Here, we have noticed that the number of terms appear in this expression is 1, 2, 3, 4, 5, 6. We know that the permutation of three numbers, distinct numbers, now we are about this 1, 2, and 3 distinct numbers. I'd like to list the three numbers in order. For example, the first one, there are three numbers available, 1, 2, and 3. And then I have the three cases for the first blank. And what about the second blank? Because I have chosen 1, 2, or 3 already, In this case, I have only two cases left, that is either 2 or 3. So I have two multiplicities. And after that, if I fill the two blanks already, the remaining one is completely determined. As a result, I have a 3 times 2 times 1 distinct order. Therefore, we say this one to be the permutation. Permutation. We find that the indices for E something, A something, and B something, they have their own a vector index that is one of 1, 2, and 3. And these are 6 permutations. Very important to see from this expression is that we have 3 sets. But this 3 has a positive sign, and these 3 have negative sign. For simplicity, we call this even permutation, and we call this the permutations with the negative signs the odd permutations. All right, even permutations are 1, 2, 3, 2, 3, 1, and 3, 1, 2. For the vector index for E, and vector index for A, and vector index for B. So these 3 permutations are called even, and remaining 3 are 1, 3, 2, 2, 1, 3, 3, 2, 1. So we find the last 2 digits are exchanged to have a negative sign. They are called odd permutation. Okay, so we have found one of 8 vectors, plus minus, and plus minus. So we have chosen positive sign, and after we list all possible cases with a positive sign, this special vector is expressed as a linear combination of a 3 Cartesian unit basis vector, and whose components are products of 2 Cartesian components, A something and B something, and vector indices for the unit vector and A and B construct 6 permutations, and among 6 permutations, we have 3 permutations with a positive sign that is called even permutation, and the permutation, 3 permutations with negative sign in front of it that are called odd permutations. Okay. This is the mathematical feature of this special vector. Later, we will call this one to be the cross product of 2 vectors A and B. Okay, what about the scalar product of n and a vector A? If I multiply A as a scalar product to this vector n, what I find is, first, this x component is multiplied by this, y component is multiplied by this, and z component is multiplied by this after erasing this. And all of the crossing term vanishes because ei hat dot ej hat equals either 1 or 0. If I and j are the same, we have unity. If I and j are different, they vanishes. Therefore, we find that the expression for the scalar product of n and a is like that. We notice that if I expand everything altogether and we find a1, a2, b3 is positive, and there is another. What's that? A1, 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 A2, B3 is this. A1, A2, B3 is there with a negative sign. So this one comes here, and they are identical to each other except for the sign. They cancel exactly. A2, A3, B1 is here. So I have erased these two, they cancel. A2, A3, B1. Is there any? Yes. I have copied this one here. A2, A3, B1 is also there with the negative sign. So I cancel this. They are identical to each other. They cancel exactly. And then remaining two terms, A1, A3, B2, that has a negative sign, A1, A3, B2, that has a positive sign. In a similar manner, all six terms cancel exactly to find the scalar product between n and a is 0. In a similar manner, n that b is also 0. What does it mean by n vector scalar product a equals 0? We know, in general, the magnitude of this and magnitude of this, both of them are non-vanishing vectors. In that case, they are proportional to the magnitude product of the magnitudes and then cosine theta. This one states that if the magnitudes are all non-zero, cosine theta must vanish. That means these two vectors are perpendicular to each other. All right. As a result, in a similar manner, n dot b equals 0 states that later we will call this one as scalar vector product or cross product of a and b. This one is perpendicular to both a and b. That means a parallelogram is on a plane, and the cross product has a magnitude that is proportional, that is the same as the area of the parallelogram, and the direction of the parallelogram is perpendicular to the plane on which both two side vectors a and b are placed. So they are making a right angle with the plane on which the parallelogram is placed. All right. A is an arbitrary vector in 3 dimensions. I'd like to read off the first Cartesian component. Then I multiply the unit vector E1 hat as the scalar product because A equals A1 E1 hat, A2 E2 hat, and A3 E3 hat. We know EI dot EJ equals chronicle delta IJ. That is 1 if I equals J, 0 if I is not equals to J. Therefore, if I multiply E1 dot, this term survives own and remaining two pieces vanishes exactly. In a similar manner, any Cartesian component of vector can be read off from vector A by multiplying a unit Cartesian basis vector as a scalar product. In addition, this one, Cartesian component multiplied the corresponding unit vector is a component vector. So this one is x component vector of A, and this is a y component vector of A, and z component vector of A. If we are restricted to the three-dimensional Euclidean space only, then all of the Cartesian components consist of the three components only. As a result, any vector can be expanded as a linear combination of three unit Cartesian basis vectors. This is called completeness relation. We don't miss any part of a vector in three dimensions if I use this expansion formula. We have unit vectors E1 hat, E2 hat, E3 hat as a basis vector, and coefficients are called Cartesian component, Cartesian coordinates, something like that. And these are all uniquely defined because these three vectors are linearly independent. They do not overlap at all. As a result, we had better remove this general notation and choose a specific coordinate dependence. And actually, when we learn from elementary school to high school, we have never introduced this method. Instead, we use some ordered pair of numbers x, y. These are the Cartesian coordinates. What we have done is neglected this one, and actually we replaced this one with a specific matrix form that is called matrix representation. So, ordered pair or n tuples are all a kind of matrix representation. Matrix representation means nothing but a list of coordinates without displaying the basis vectors. Okay, so why don't we write this one as x comma y is a sum of x 1 0 plus y 0 1. So this is what we are considering as E1 hat, and this is E2 hat. In three dimensions, there are three components, and any Cartesian unit vectors along the x-axis, y-axis, and z-axis are expressed as a column vector. This is a list of numbers. This is a kind of column, so we say it is a column vector. Column vector whose first, second, and third elements represents the Cartesian coordinate. And E1 hat is the basis of the x coordinate. So what we write to represent this unit basis vector is 1 0 0 for E1, for E2 0 1 0, E3 0 0 1. What we write in here is in a row representation, and this is column representation. In case depending on the case, we will write it in terms of column or row. But as a first step, we had better begin with the column representation when we write a vector in terms of matrix representation. Okay, E1 hat is 1 0 0, E2 hat is 0, 1, 0. E3 hat is 0, 0, 1. Why don't we introduce the row representation, neglecting, suppressing the commas? So this is a column and this is a row. If I want to replace this column representation with the row representation, we attach a special notation as a superscript that stands for the transpose. Transpose is to transform a column into row and a row into column. For example, if I attach this transpose operator on top of the right side of a row, then it converts a row representation of a vector to a column. In addition, a row, after transposing, it becomes a row, and again I apply the transpose operation, and it flips again to a column. So double transpose is nothing but the identity transformation. Keep a column as a column and keep a row as a row. For Cartesian representation of the scalar product, we remember the scalar product A dot B is expressed as the sum of products of each Cartesian components. This is based on the fact that EI, EJ hat scalar product is canonical delta IJ, and that is 1 for I equals to J and 0 for I is not equal to J. As a result, we can find the scalar product not based on the exact original definition, but by making use of the Cartesian components. It is a very, very convenient in general case. In a case, if you know the angle between the two vectors and their magnitudes explicitly, this original definition is quite useful. However, if in general, it's better to make use of Cartesian components. And we know the Cartesian basis vectors are orthogonal to each other, so it is very useful to express the scalar product in terms of Cartesian components. Why don't we make use of matrix representation to express the scalar product? Let's see. We define this one by, we know they are the same, and we define this row vector multiplied by the column vector by this. That means multiply the first element of the row and first element in a column. And the second, third. Multiply this multiplication, and this multiplication. And A1, B1 is written in here, A2, B2 is written in here, and A3, B3 is written in here, and sum them all is called the product of a row vector and a column vector. So it is just definition. We define this form of a list of numbers, row first and the column next. And this is a multiplication of row vector and column vector. First multiply, second multiply, third multiply, and sum the products all. Then this is identical to the scalar product expressed in a Cartesian coordinate system. Based on the definition of a scalar product, we find the scalar product is commutative. As a result, it is trivial to note that exchanging this row and column, exchange it to here. This column is replaced with row, and this row is replaced with column, and the final result is multiplication, 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 sum. Multiplication, 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 sum. They are the same. Why? We define this product to be the scalar product, and the scalar product is commutative by definition, and as a result, it is trivial to notice that exchange row and column in a product doesn't change anything about the result. Next, we consider the equality of two matrices. Now, matrix is nothing but a collection of rows or a collection of columns. For simplicity, we have two row vectors or two column vectors combined as a list of numbers, or array of numbers, surrounded by parentheses. And we say they are the same in case this first element, we say the first row and first column. This element at the same position, they are the same. First row and second column, first row, second column, they are the same. Second row and first column, second row and first column, a B and Y, that's the same. And the second row and second column, a D and W, are the same. Transpose is also applied in similar manner as we have defined for a single row or single columns. That's nothing but to replace a row into a column, row into a column, vice versa. In general, if I exchange this row and column, the shape shape is not invariant. Only the diagonal elements are invariant, but this one off diagonal, this is diagonal, and this is off diagonal. Off diagonal elements are exchanged. As a result, in general, the transpose of a matrix is not invariant. So they are different. It is different from the original one. However, if I have only a single element in a matrix, that is one by one matrix, if I have m rows, n columns, then we say m by n matrix. But if I have a one by one matrix that is just a number surrounded by the parentheses, it has only a single element that is a diagonal. Therefore, the transpose is identical to itself. It's a special case. In general, if I have a product two matrices, the transpose can be computed in similar manner as what we have done with the scalar product commutative law of a scalar product. I have exchanged this row as a column, exchanged this column as a row. What I have found is this one has been transposed, and this is put to the right side. So this A and B, this is a row vector, and this is column vector, but this one is replaced, the B and A, and this one used to be a column, it is a row. I have to attach the transpose, and this one is this, something like that. So what I have done is product of A, B's transpose that is identical to transpose B multiplied by transpose A. Explicit computation can be found in here. This is a nice exercise. All right, that's it for today. Thank you.